Ever wondered how to build a cardioid USB high sensitivity high bandwidth condenser transducer based microphone? No? That means you're a normal person. Good for you. But for any other weirdos out there, here's how I built mine. Maybe you've noticed this is my third video. I started making videos quite recently, and I did not invest a fortune in equipment. I'll do that after I'm famous. So, for now I use things lying around, like a DSLR camera, everybody has one somewhere in a corner, my PC of course, and a sound recording device, a microphone. When I chose my microphone, first I tried with a headset. It was horrible. Then I soldered the microphone to a board I've been working on for the past year, added a piece of paper, and done! I got my recording microphone. With some help from a noise reduction software, it became quite acceptable, and for the moment I am still using this setup. But I decided it was time to move on, and since my finances didn't let me buy a proper microphone, I decided to build one. Let's see what happens. Okay, so let's talk a bit about what makes a cheap microphone bad. It's not the bandwidth, or the maximum sound pressure, the directional pattern, or any other fancy parameter. It's the noise. The first complaint when making a review about any microphone is the noise, and how much of it there is. Before attempting to build a microphone, it is important to know where all this noise is coming from. Let's look at the components of a sound-to-digital audio system. First, we have the sound generator, obviously. Then, a sound transducer, the microphone component. This turns sound waves into electrical signals. We then need an audio amplifier. This is needed since the signal from the microphone is very small, in the order of millivolts. Then, the amplified audio signal is digitalized by an ADC, an analog to digital converter. And from there, it's no longer our concern. But one more thing has to be mentioned, the power supply, because all of the above components need power. So let's see the noise sources. Where is all the noise coming from? It's not from aliens or cosmic rays, it's actually from measurable sources. First of all, the mentioned components have an internal noise. The microphone is characterized by its signal-to-noise ratio, the amplifier has a noise density parameter, and the power supply has an output voltage noise. Then there are external noise sources, and here we have electrical sources, either electromagnetic radiation, which will impact especially the microphone amplifier connection and the amplifier ADC connection. Then there is the electrical noise on the supply lines, which if not filtered will be directly fed into the microphone and amplifier. It is important to mention here that if we wish to use the USB as a 5V supply, we will have a lot of headaches, since this supply is extremely noisy, and a lot of filtration will be needed. And finally, we have mechanical noise. Background noise, like my neighbors. We have vibration-based noise, like when a truck is passing in front of my window, and reflections, echoes of the primary sound I wish to record. Oh boy, sounds like a lot of work to pull this off and actually do a proper job, but that makes it a proper challenge, so let's do it. Okay, we have all of our noise sources. Let's see how to eliminate them, or at least reduce some of it. I will start with the last one, the mechanical noise. To reduce the effect of background noise and echoes, you first need a proper recording studio, or at least a quiet room. Then, you need to make the microphone directional. For that you can add a funnel to extract only a certain direction of sound. Afterwards, for the vibrations, the sound transducer can be suspended by springs or other soft materials. These will absorb most of the unwanted interference. For the electromagnetic influences, the easiest thing that can be used is putting the entire circuit inside the Faraday cage. The part that needs to be permeable to sound will have a wire mesh, and the rest a solid box. For the supply noise, well, a good supply is required, with a lot of filtering. And finally, the internal noises, well, more expensive components are better components. It's that simple. Just check in the datasheet the parameters. Looking much better now. In this video, I will only present how I designed this area. I will discuss the rest also, but I will go into more details next time. Okay, finally, time to build something. No wait, I still don't have a schematic. Oh look, now I do. I know my microphone transducer has a minus 35 decibel sensitivity. That means that for 1 Pascal sound pressure level, I get about 17 millivolts. My amplifier will need to increase this voltage to a level that satisfies the ADC input. As ADC I am using the PCM2903 IC, which has a maximum input voltage of 1.9 volts. So I need an amplifier that boosts with a factor of 117 to fully drive the ADC, although 100 amplification will do. As amplifier, I chose the OP27, a low noise amplifier. The choice of amplifier will influence the power supply. For this IC, I have a common mode input voltage range of 4 volts away from the supply lines. And I want about 2 volts of output voltage swing, so I need to supply the amplifier with a minimum of 10 volts, after filtration, from a 5 volt USB. This will be fun. Okay, I need a voltage reference now to have my circuit centered around something, and 10 divided by 2 is a very common 5 volt, so a linear regulator will give me my reference. I will use this supply network also for the microphone. Seems simple enough. I was talking to a friend about ordering the microphone transducer and he was like, "But I have a whole box of them, why bother ordering?" And I remembered, I also have a box somewhere of old microphones from various headsets and other things, but I have no idea of any of the parameters of those devices. The things I was looking for when I chose this particular component was the high sensitivity and the good bandwidth. Why? Well, the more sensitive it is, the less amplification is needed, and the less you amplify the useful signal, the less you amplify the unwanted noises. And regarding the bandwidth, the component I'm using has a 50 Hz to 16 kHz bandwidth. This will be able to process almost the entire audio range, and definitely the entire voice spectrum. So this particular microphone will fully satisfy my needs. Looks nice when assembled. As said previously, I will not insist on the rest of the circuit this time. I will just take this thing and use it for initial tests. This contains the ADC, supply network and any other needed components. And let's see if the microphone amplifier bit works. For this part, I will not be using any noise suppression software. As comparison, this is how my current microphone sounds like. Can you hear all the noise? Good. And now, time to test the new microphone. Hello? Can you hear me? Is it any better? Let's quickly compare the two. Before and after. I think I made a good improvement. But it's not perfect. So let's try to identify where the noise is still coming from. First, let's hear the ADC with nothing connected to it. Perfect silence. Good. No noise is coming from the ADC. Next, I will connect the amplifier without the microphone. This will show us how much noise is in the amplifier and supply bit. Amazingly, not a lot. And finally, time to add the microphone. So here is the main source. Well, it must be mechanical and some electromagnetic influence. Well, unfortunately that will be all for today. I will be looking into all the countermeasures discussed earlier and I will get into more details with the rest of the circuit next time. I hope you enjoyed this video, leave your thoughts in the comments and see you next time. Bye bye.